Okay, we're going to continue on here, and we got into obviously last time the first chapter. Flip that around. So chapter 12 and equilibrium. And as we talked about last time, equilibrium really involves a specific type of reaction, and that is a reversible reaction. So as we talked about last time, those are reactions that basically head in two directions. It has reversible arrows. So again, it is different than just a non-reversible reaction where we just have one arrow where everything's kind of dumped out to the products. Here we do have a reversible reaction, as we talked about last time. Heading from reactants to products is our forward direction. Heading from products back to reactants is our reverse direction. And remember that basically this type of reaction will come to what is referred to as chemical equilibrium. And as we talked about last time, again, sometimes people have a misunderstanding about sort of what that means. Remember, it doesn't mean that we have equal amounts of everybody on each side of the arrows, but really what it's referring to is the rate and really kind of the kinetics there. The rate of the forward direction will equal, again, the rate of the reverse direction. And that is essentially when equilibrium has been reached, as we saw sort of in some of those graphs, and as we also talked about, essentially what happens when we do reach that equilibrium condition is it will essentially lock everybody into place in terms of their concentrations, or again, if we're perhaps dealing with pressures, what their pressures will be as well. And that's again because just as quick as it goes to the product side, those products will basically recombine and go back the other way. So net wise, nothing's really changing in terms of the concentrations of the reactants and the products at the point when you've reached equilibrium. Remember as well that when you look at something that's at equilibrium, sort of in the big picture sort of view of it, it may look like not much is happening or it's over and nothing else is going on. But remember, if you kind of super zoom in, to the microscopic level, there's a lot of activity. You have constant movement happening in the forward direction and the reverse direction. Again, they just happen to be equal to each other. So net wise, it does not appear that much is going on, even though there's a lot going on to maintain that. Now, it will basically keep at equilibrium until you do something, for example, to kind of screw up the equilibrium. At that point, it will, as we talked a little bit about, and we'll talk more about towards the end of this chapter, these type of reactions will always want to get themselves back to equilibrium. So even if you kind of screw it up, it will actually sort of self-correct itself, make some adjustments, and it will eventually be able to get back to that sort of condition of the rate of the forward direction equals the rate of the reverse direction. When we look at an equilibrium reaction like this, we could write what is referred to as the equilibrium constant expression, and that is basically our K value here. And that is our equilibrium constant. And as we talked about, it is a constant value for a reaction exactly the way it's written under those particular temperature. And as we also talked about, temperature is really the one thing that can actually affect the value of the equilibrium constant. But if the temperature remains constant, then the equilibrium constant value should be the same. And again, as we talked about, regardless of what you start with, it should come to rest at the same proportion of products to reactants. And that is how we calculate an equilibrium constant. Is we take basically the concentration of all of our products divided by the concentration of our reactants. And when we do so, that is sometimes referred to as the Kc value when you use concentration. Remember, though, that when you do write that, you do have to take into account the coefficients in the balance equation. They become the exponents. So it is important that you do that relationship as well, where you take the coefficients up there as those exponents. Now, we could do it with concentration like we talked about. If you do have gases involved, oftentimes we measure more pressure in some situations like that rather than, say, gases molarity. We could write as a similar type of expression, which is known as Kp. And it is still products over reactants, but we do the partial pressure of our products, basically, divided by the partial pressure of our reactants. We still take the coefficients just like we would here. So this would be our Kc. Our Kp would be the partial pressure of C to the C, partial pressure of D to the D, partial pressure of A to the A, and partial pressure of B to the B. And you basically do that. Remember that in most cases, if you're doing some type of calculation involving equilibrium, standard sort of units that we use in these calculations for things like solution and molarity, our concentration is molarity. And also for pressure, typically atmospheres is sort of the standard sort of pressure unit that we use in equilibrium calculations. We saw there towards the end, there is a relationship that you could go between the Kp and the Kc. And that formula again is Kp is equal to the Kc RT delta N. Again, this is your Kp value, your Kc value. Your R is your gas constant, like the one you use in the ideal gas law. The temperature, like kind of most gas sort of formulas, doesn't need to be in Kelvin. And delta N, there's a change in the number of moles of gases. So that's the moles of the product minus the moles of the reactant. Here, obviously, we'd be looking at only things that are gases to be put into there. Remember that K does tell us some information, and it is a value that does not have units typically associated with it. So it is just a number. And remember that, again, if we have sort of a large value of K, that means that we would expect mainly products to be present at equilibrium. Again, just mathematically speaking, large number on top, small number on the bottom gives us a large value for K. And obviously, as we also talked about, if you had more of a small K value, then you would expect more reactants at equilibrium. Same math-wise, smaller number up on top, larger number on the bottom is going to give us a smaller number when we divide those two together. Any questions on any of that stuff we talked about last time? All right, then let us continue on. And one of the other really important things that we talked about in terms of writing equilibrium expression, thank you, is there are a couple of things that we do not include in the equilibrium expression. And these are the two things really that we don't. And that is something that's a solid or anything that is a pure liquid. So remember that when you go to write your K value, we not included anything solid or liquid. And again, included in our K value would be what is left, which is essentially gas and aqueous solutions. So in this case, if we were to write our equilibrium expression, we would do our products over our reactants. Once again, the concentration of these guys is going to remain the same because they're solids, so we actually don't include them. And that would get us really our proper equilibrium expression for this reaction, which again would really just be the product side in this case. Because this is a gas, we definitely can write also a Kp type expression for it. And it would also just be our CO2, as again, the other ones there are solids in this particular case. So anything with a solid, anything that's a liquid, you just leave out. And then most times in calculations, you ignore it in a sense of calculations because it really will not participate. Again, as I might have mentioned last time, the solid is just kind of sitting there, not doing very much, and liquids have a fairly high concentration, pure liquids, and it doesn't change all that much throughout the process like something like water, so it's not really included. In order for a solid to really sort of participate, if you will, it would have to like dissolve, and at that point it's no longer a solid. It'd be something maybe like an aqueous ion if it's in solution or something like that, and at that point those ions would participate in the equilibrium. Yes, sir. They only be HC, or can they be as well? Yeah, so typically speaking, KP deals with only pressures, so you would just do the pressures in that situation, yeah. Yeah, so in most cases, the combination that you probably would get would be something like what we see here in this particular problem, a solid that would go into the gas phase, like in a decomposition reaction. You typically wouldn't see, in most cases, like a solid kind of like, or, a gas and maybe aqueous together, because the gas is going to kind of leave that part of it. Yeah. Other questions? And again here, really, as you can kind of see, the solids here are just sitting on the bottom. They're really not participating as we see our gas molecules flying around and participate in this equilibrium. So the pressure of the CO2 is not dependent on those solids. Again, obviously, it's the amount of gas that is present in that situation. And as you see, even though we kind of changed the amount of solid that's there, the pressure here remains the same in both situations, so it has no real effect on it. As obviously pressure is just affected on gas molecules that are basically moving around. All right, so let's try one here. Consider the following equilibrium. The partial pressure of each gas here is 0.265 atmospheres. Calculate the Kp or K and Kc for this reaction at 295 Kelvin. So see what you come up with here. Take a few moments. Okay, so let's take a look and see. So once again here, we want to kind of think about the information given to us as to where a good starting point would be. Here I am given some pressures. So to me, Kp seems like the good one to go after first here. So we'll start with our Kp expression. So we're going to go partial pressure of NH3 times the partial pressure of H2S. Here, this guy is a solid, so we will not include it, obviously, into this expression. Each of the gases are 0.265, so basically 0.265 times 0.265. That is going to give us our Kp value here of something. What we got there? We got 0.265 squared. All right, we got call it 7.02 times 10 to the minus 2, or 0.0702. That is going to be our Kp value. Now, again, we have our Kp value. We could use that formula that relates the two together, and we could take our Kp is equal to our Kc RT delta N. Here, our temperature was already in Kelvin, so we're good to go on that. R is obviously a constant. We do want to calculate delta N, so it is our product, which is one gas molecule, two gas molecule, minus our reactants, which is no gas molecules. So N in this case is going to equal 2. And I think what might be all we might need here. 7.02 times 10 to the minus 2 equals our Kc. 0.08206 times our temperature of 295. And again, here we're going to square it. So we'll take 0.08206, we'll times it by 295. We will then square it. And that's going to give us roughly here 586.01274. We need to then take this guy and divide it right to the other side there so that we can solve for Kc. And that is going to get us here a Kc that is equal to 1.20 times 10 to the minus 4 in this particular case to go with this guy. First off, any questions on any of the calculation there? As we also talked about last time, usually the Kc and Kp value are not numerically the same value. They can be in a rare instance, but they should again agree in terms of large or small. So here we do have a small Kp value and also a small Kc value. So again, that is a good thing. You don't want like one small and one large, because that would not make sense in this particular case. Any questions on that there? All right, so the next thing we're going to talk about is equilibrium constants and equations, and what happens when we maybe manipulate those equations. So either maybe we add them together, maybe we reverse a reaction, whatever it may be. So in this particular case here, we have one reaction here with a Kc, which is our products over our reactants there. So our C times D divided by A times B. Here we have another equation there, also products over reactants here, getting our K value for that equation, which is E times F divided by C times D. As you may be familiar with, not all reactions do occur in like a one-step process. Sometimes it's multiple reactions occurring that leads you to the overall reaction that you're looking at. If we were to basically add both of these reactions together, and when you do add reactions together, anything that's on opposite sides of the arrow that's the same could either cancel out completely or reduce down. You think of the arrow almost like an equal sign, like you're subtracting it to the other side, basically, is sort of the idea there. And then at that point, whatever is left, everybody on the left stays on the left-hand side of the arrow, everybody on the right stays on the right-hand side of the arrow. And that would give us this overall reaction here, which we could actually write an equilibrium expression for this overall reaction, which would be E times F divided by A times B. In this particular case, we added these two reactions. What happens with the K values is we actually multiply them together. These guys cancel. What you're left with is over here. So if you have to add one to however many reactions together to get an overall reaction that you're looking for, you basically take all the K values and you just multiply them together. So you do not add, which is a common error people do. They want to add them together. Here you do multiply K values. We'll talk about when we get to thermodynamics, delta H's and stuff like that. There you add, but here we do multiply these guys together to get the proper sort of reaction when it's all said and done. Any questions on that there? So that is obviously a very common thing that could occur. Another couple common things that you could do to these type of reactions is, for example, maybe you don't need the reactants on the reactant side, but you need them on the product side and vice versa. You can reverse a reaction like we see here. And when we reverse a reaction, if we have this reaction written as so, we take our products over our reactants and we get our K value. When we reverse this reaction, we actually get this as our equilibrium expression, which is the N2O4 divided by the NO2 squared. It is actually 1 over the equilibrium constant value. So if you have to reverse a reaction, you take 1 over the K value, and that will get it for you the correct one. Again, common mistake people make when they do this is they just change the sign. So again, not in this situation, thermodynamics, that's what you do, but here, our reactants become our products become our reactants. So our fraction basically just flips, basically, right? So we got to take 1 over the K value to do that. So again, that is a very common sort of thing. Also, when you do see a K value written, for example, this number here, that is specifically the value for this reaction exactly the way it is written, with the N2O4 as your reactants and the NO2 as your products. If you say the K value for this reaction is 216, that is specifically for the way this reaction on the right is written, with the NO2 as the reactants and the N2O4 as the product. So when you see a K value, it is specific for who's on the reactant side, who's on the product side, the way it is written. And if you technically kind of flip the reaction, you need to inverse the K value. So if we add reactions together, we need to multiply K values to get the overall K value for that reaction. If we reverse a reaction, we need to take 1 over the K value. A couple other things that you do come across is, for example, let's say we had this reaction here. And our K here would be again C and D divided by A and B. Let's say though that we did not just need one A, but maybe we needed two A's. And what that would require us to do if we needed two A's is we would have to multiply that entire equation, not just A, but everybody there by 2. And that would get us 2A plus 2B goes to 2C plus 2D. If I write the equilibrium expression for my new reaction here, that is C squared D squared divided by A squared and B squared. What happened to my K value as it went from here to here? It went up by what? What did we do? We basically squared it, yeah? So we multiplied by 2, so we have to take the K value to the second exponent or square it. By the way, if I multiply by 3, I would then cube the K value, yeah? So if you multiply by 4, you would take it to the 4th power and so forth. So if you have to multiply by a common number, you take the K to that common number is how you adjust it. So again, like I said, if you multiplied by 3 in this case, instead of 2, you would take the K value and you would cube it as well. So that is a very common sort of manipulation of K values. Also very much screwed up by people because they will actually just multiply 2 times the K value instead of, for example, squaring it or cubing it, they'll time 3 times it. So you got to do that. Obviously, the last sort of adjustment that you can kind of make is if, let's just say we actually started with this guy and we wanted to get to this guy, which is kind of like our original sort of equation. And if we do that again, I'll call it 3. We will end up with C and D divided by A and B. So as we go from here back to here, I basically divided by 2 all the way across. And because I divided by 2, I actually took the square root here of this particular K value. So if you divide by a common number, you actually take the root of the K value to that common number. If I divided by 3, I would take the cube root and so forth as you go through there. So if you divide by a common number, you take the K value to that common number, sort of root of it to there. So those are 4 very common ways that you can sort of manipulate equations. This would be something very similar to what's known as Hess's law, where you kind of build an equation from some other equations. The key here is to keep track of what you did, adjust the K values accordingly, and then obviously multiply them when you put them together and you add up those equations. Any questions on that there? Yeah. You take the cube root. Yeah, yeah. So whatever you divide by goes right there into your root sort of thing. Yeah. So if it's 2, it's the square root, 3, it's the cube root, and so forth. And it's kind of the same idea here. Whatever you multiply by, you take it to that power, basically that number. Other questions? All right, so why don't you try one here? Let's say we wanted to know what the K value is of this top equation using these 2 guys down here. So take a moment, rearrange them, put them together so that you end up with the top equation, and then calculate what the K value would be for that top equation. Really just trying to kind of build the top equation from these 2 guys. Probably the easiest approach is to kind of keep it simple and just get everybody on the correct side where you need them. So for example here, I need E and F on the left-hand side. I obviously have E and F in this equation. It's on the right-hand side. So I know for sure I need to reverse it to get it to the other side. I also not need more than just one of them, right? There are 2, so I need to reverse it and also multiply by 2. So this one for sure, I need to kind of reverse and then also times it by 2. So that is what I'm going to do. So I'm going to reverse it here, which would give me E plus F goes to this, bless you, C plus D. I am also going to multiply it by 2, which is basically going to put a 2 there in front of everybody. Now, the important thing here is to keep track of what I did now to my K value. So the first thing I did to my K value is I reversed it, which means I need to take 1 over my K value, right? Then I also multiplied it by 2, which means then I need to take that and also square it as well. So again, that's important to keep track of. At this point, that gets me these guys on the correct side. I need A and B over here on the right-hand side. A and B is in this equation, but it's on the left-hand side. So I know I just need to basically reverse the top equation. That will get me my 2C plus 2D goes to A plus B. Once again here, now thinking about how that affects my equilibrium value, I reversed it, so now I need to take 1 over the K value as well. So if I did that, since I'm out of equations at this point, I hopefully should end up with the equation I'm looking for. Everything on opposite sides that's the same could either fully cancel out or reduce down. So those guys will cancel. These guys here will cancel. Everybody on the left-hand side will stay there. It gives me 2E plus 2F. Everybody on the right-hand side will stay there. And again, I have now really built the correct sort of equation I'm looking for. At this point, I want the K value for this guy. I'll just number these 1 and 2. At this point, I'm going to basically take K1, and remember here, we're going to multiply it by K2, not add it together. So we get some numbers there, 1 divided by 20, and then squaring it is going to get us here 0.0025. Over here, 1 divided by 100 going to get us 0.1. So again, we're going to go 0.0025. We're going to times it by 0.1. And that's going to get us here a lot of zeros, 0.000025 as our overall K value. Obviously, because done a little scientific notation now. Not wrote so many zeros, I suppose. Any questions on that one there? So again, just trying to get everybody in the correct side of the arrow is a good approach, and just kind of take it step by step and figure out what you need to do. All right, let's take a look at another one here. Why don't you try this one? We're looking for the bottom equation based off of the top two. So see what you can look. Again, we'll take the same approach, just kind of get everybody on the correct side. So I'm just going to start here with N2, which is on the left. And really the only equation that has N2 is the top one. It is on the left. The deal here, though, is I need 2 of them. I have a half, bless you. So I don't need to do any reversing of the first one, but I do need to multiply it by a number to get me 2. And in that case, I actually need to multiply by 4 in this case. I'm going to rewrite it somewhere. I don't know. Maybe I'll go high on it. I'll rewrite it up here, I think. So that's going to give me basically 2N2 when I multiply that by 4, 4 divided by 2, plus 12 divided by 2, which is 6H2, and 4 times 1 is 4NH3. In this case here, because I multiplied by a common number of 4, I will have to take my K value to the 4th power in this case. Again, we're not going to multiply the K by 4. We need to actually take it to the 4th power. Any questions on that one there? If I look at my next thing that I need, which is water, it is on the left-hand side, which it is here as well. But again, here I need 6 waters. I only have 2. That is going to require me to multiply the second one by 3 in this case. Again, doing that up here on top gets me 6 waters, which is what I need. And no pluses, just some arrows, I think. Then coming across to the other side there, 6 H2s and 3 O2s. Here again, I didn't reverse or anything like that, but I did multiply by the common number of 3, which means I do need to take the K value there and cube it at this point. I'm out of the equation, so we're going to add these together and hope we hit the one we're looking for. 6H2s on the left will cancel out the 6H2s on the right. And I think that is all the canceling. That's going to give me 2N2 plus my 6H2O on the left. And on the right, we'll have my 4NH3 and my 302, which is this equation here on the bottom. So we did everything good. Any questions on that there? Obviously, once again, at this, yeah, you should question. Okay. We do, yeah. So we can do that right now. So at this point, we want the K value obviously for this. So we do need to combine them. So I'll just put some numbers here. We're going to take our K1 times our K2. Once again, we need to obviously do our adjustments to each of those. So we'll take 411 and I'm going to take it to the 4th power there. And that gets you something like 2.85 times 10 to the 10, actually. 85 times 10 to the 10, I think. And we'll take 0.345 and cube it. And that's going to get you something like 0.041. We are again going to multiply those together, not add them. And if we do that, we do end up with a ginormous number. I'm going to go scientific notation on it, I think. We'll go 1.17 times 10 to the 9 in this case. Looks like a winner. Yes, sir.
For the K, when you're finding like the K value, do we always multiply our K1 and K2 or?
You do in this case because in order to get to this equation, it was a result of adding these guys together. So when we add equations together, we multiply the K values. By the way, we only did 2 here, sort of equations, but if you had 3 or 4 and you had to add them all together, you would multiply all of those together. So it doesn't matter how many you have. You just keep basically multiplying the K values if you add those equations together. Other questions? Yeah. We typically wouldn't subtract. We typically would just add it in this situation. Yeah. Because the idea is to put these equations together, these reactions together to basically make the overall reaction that's happening, because it does occur in multiple steps. And because it occurs in multiple steps, basically each of those steps are added together to get the whole. So we never would subtract. The only sort of subtraction we do is getting rid of things we don't really need by rearranging them on opposite sides so they cancel out correctly. Gotcha. And really what's canceling out, for example, the things that we're canceling out here, for example, these are what you might remember from kinetics is what are sometimes referred to as intermediates. Yeah. And intermediates in our chemical reaction are things that are produced like early on in the reaction and then get used up by the time the reaction's over. And that's why they don't appear in the overall reaction. So that's kind of what those things are that kind of gets used up. Any questions? All right. All right, so as we've been seeing here and been talking about in sort of these examples, if you do manipulate an equilibrium sort of reaction, you do have to take into account the effect that has on your equilibrium constant for your new equation. Again, we don't include, again, any solids or liquids. It is only a number of the equilibrium constant value when it's all said and done. And remember, these are really your go-to units if you're doing some type of equilibrium calculation. We want molarity for concentrations and pressures, atmospheres. As we just saw there, if you add together some equations, multiply the K values. If you reverse an equation, 1 over the K value. And again, if you multiply, take the K value to that number, or if you divide by a common number, take the root of the K value to that common number. We talked about a number of times sort of this idea here in this slide, but again, just to reiterate, the temperature is, again, the only thing that changes that actual value of the K, the equilibrium constant. And remember that what we're talking about when we say that is the comparison of the K value at one temperature versus the other will be different. Again, like we talked about last time, if you ran multiple experiments at a constant temperature, the K value should be the same for all those experiments. Even like it says there on the bottom that, like we saw, if you started with all reactants in one situation, all products, a little bit of everybody together, they all should come to rest at the same ratio of products to reactants. So the next thing we're going to talk about is a different letter, believe it or not, is Q. And Q is the reaction quotient. And the reaction quotient is calculated, or Q is calculated the exact same way as you calculate the equilibrium constant. So if you need to calculate Q, you basically do exactly the same calculation as you do K. So Q is our concentration of our products divided by our reactants, or obviously if you're doing pressure, the pressures over the products over reactants as well. So you may be asking yourself if Q is calculated the exact same way as K, and by the way, you do the exact same thing. You still use the coefficients as the exponents, just like you do in K. Why do we have Q versus K? So really what Q is it answers really two questions for you in a situation. What Q answers is this. It answers the question of, are you at equilibrium? So is this system currently at equilibrium is what Q basically tells you. We typically use Q for initial concentrations, like if we're not sure if we're at equilibrium or not, we could calculate Q. And if we know the K value, we could then determine whether or not we are at equilibrium. The second thing that Q will tell you is if you are not at equilibrium, it will tell you which way you need to go to get to equilibrium. Do you need to make more products? Do you need to make more reactants to actually get this system to equilibrium? So Q is used in a couple of different situations. I would say most often Q is oftentimes used in what I call just a straight up Q type question. Like it's asking you, is this thing at equilibrium? And if not, which way to go? That's very commonly the way you would calculate Q for. There is another situation later on where you will perhaps need to calculate Q, and that will help you determine which way the reaction is actually proceeding. So when we get into equilibrium calculations, you sometimes will have to calculate Q in addition to the equilibrium calculation to help you verify which way the reaction is actually proceeding. If you calculate Q and it is greater than the K value, then the reaction is not at equilibrium. In order for it to reach equilibrium, it goes the opposite way of that thing where it's pointing. It goes towards the reactant side. So you need to make more reactants. If you calculate Q and it actually does equal the equilibrium constant value, congratulations, you're at equilibrium, basically. That was what you're at, and that's the goal. If you calculate Q and it's less than the K value, you are not at equilibrium, and it goes opposite the way this guy is pointing, and it needs to go to the product side to reach equilibrium. So if you put Q on the left and K on the right, it goes opposite the way the greater than sign is sort of pointing, is which way it needs to go in the reaction. So like I said, this is kind of two situations where you calculate Q. Because Q is calculated the exact same way as K, that means the only way that you're able to ever calculate Q is if you have all the information about everybody in the reaction. So if you're only given like reactants, there's no way you can calculate Q because you have no information about the products. If you're just given products, you can't really calculate Q because you don't know about the reactants. But if you see a problem where you have basically concentrations or pressures of everybody, that is a situation where you can calculate Q because you have all the information to do so. So why don't you try one here? Let's say we had a reaction like so. We're starting with 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2, and 6.42 times 10 to the minus 4 moles of NH3. It's in a 3.5 liter vessel. The Kc for this reaction is 1.2. The question is the system at equilibrium? And if it is not at equilibrium, which way does it need to go to actually get to equilibrium? So take a few moments there, calculate up what you think. And again, Okay, let's take a look. So once again, as I mentioned before, Q is basically calculated the same as K. So we could write our Q expression. It'll be our products in this case, our NH3. Just like we do with K, we will have to take, again, the coefficient there as our exponent, divided by our N2, which coefficient is 1, and our H2 coefficient is 3. These are concentrations. We have moles and volume given to us, so we do need to calculate the molarity of everybody here before we go in. So concentration of N2 is our moles of it, 0.249 moles divided by 3.5 liters. That's going to get us there. Looks like 7.11 times 10 to the minus 2 molar. We'll do it for our H2. There it is. And that is 3.21 times 10 to the minus 2 moles divided by our volume of 3.5 liters. That's going to get us here. Looks like 9.17 times 10 to the minus 3 molar. And lastly, our NH3 here going to be 6.42 times 10 to the minus 4 moles divided by 3.5 liters. Gonna get us here 1.83 times 10 to the minus 4 molar. Now that we have the concentrations of everybody, we can plug it into our Q. And our Q in this case would equal our NH3, 1.83 times 10 to the minus 4. Once again, we do need to square it, divided by our N2, which is 7.11 times 10 to the minus 2, times our H2, which is 9.17 times 10 to the minus 3. And again, here, because of the coefficient there, we do need to cube it. Putting those numbers in will get us that squared, 7.11 to the minus 2, and looks like 9.17 to the minus 3, and that's going to be cubed in this case. Looks like we will end up with 0.614 as our Q value. First off, any questions on the calculation? So our Q value here is 0.614. Our K value is 1.2. In this particular case, our Q value is less than K. So that tells us we are not at equilibrium, is what that first tells us, because they do not equal each other. Secondly, opposite of the way this guy is pointing goes to the product side, is where we need to go to reach equilibrium. So we need to make more products here to get ourselves to equilibrium. Any questions on that there? Yeah. Yeah, you could actually just write products, or it would proceed towards the product side. Is good. Yeah, that's good. Yeah. Other questions? Okay. So like I said, that I would say is what we would call kind of just a straight up kind of Q type question. And those are typically the two questions that you're usually asked, which is, again, are you at equilibrium? And if not, which way it needs to go basically to reach equilibrium. We will see a little later on another place where you will perhaps use Q as well. All right, then let's talk about really the calculation of the season here, which is the equilibrium calculation, and how we solve equilibrium questions and calculations. So if we are given initial concentrations, our initial pressures, we actually have to do a calculation that allows us to figure out what is, for example, everybody's equilibrium concentration when the reaction reaches equilibrium. Or again, we could also do this with pressures and calculate what everybody's equilibrium pressures would be when it reaches equilibrium. The way that we do this is we use what is referred to as ice tables. Yeah. Ice table stands for initial, change, and equilibrium. So you might have seen ice tables maybe in 200A if you did something like limiting reagents. Sometimes people will teach that. Not too many teach it that way anymore, but they could have, and then you would actually see the calculation when you knew it when you get here. But anybody learn ice tables when they did like limiting reagents? No, nobody teaches that. They should. I teach it when I teach that class. That way, when you get here, you've seen it before. But we'll talk about it here, but this is what we use, and we're going to talk about how to do it here in just a second. The idea here really in an ice table is we're really interested in the change part, and the change is typically represented with the letter X, and we use X to represent the change that's going on. Ultimately, we're going to solve for basically what X is, and that's going to allow us to figure out what everybody's equilibrium concentration is. So, for example, if you had a reaction like A plus B, actually, we'll do maybe goes to, maybe we'll do this. We'll go A plus 2B goes to AB2. Why not? We'll do that. Now let's just say the equilibrium constant for this is a 62, right? Why not? So if we were given, for example, initially the concentration of A was 4 molar, and maybe B was initially 2 molar. And that's it. We want to know, for example, what is everybody's concentration here at equilibrium? So we would set up an ice table. The first thing with the ice table is you do need a balanced equation and reaction. And if you do not have a balanced reaction, you're going to be out of luck. Yeah. So you need to have make sure a balanced reaction. We're going to start with our initial here. And initially, it is what's given to us. So we got 4 molar here. We got 2 molar here. And there was no mention of our products in this case. So if there's nothing mentioned about the products, it is fairly safe to assume that you're starting with nothing. So it's fairly safe to assume that you got 0 going on there on the product side. Now we get to the change part. And the change part is what's happening in this reaction. Now, we can safely, in this particular situation, make an assumption here that this reaction should head in which direction? The forward direction or the reverse direction? It has to really head in the forward direction, right? Because we have no product, so nobody could come back the other way yet. So the only option for this reaction is it's got to head basically in this direction. And because of that, what we do know is the amount of reactants should actually then be decreasing with time, right? Because the forward direction is happening. We should also know that the amount of products should be increasing with time because we're making products. And we represent that in ice tables with minuses and pluses. So in this case, the reactant side would be minuses because it's decreasing. The product side here would be pluses because it's increasing. We use X to represent our change. And a really important part of this is this right here. This would be minus X. This would be minus 2X. You do have to take the coefficients into account when you do the X part. That is actually taking into account the mole-to-mole relationship, the stoichiometry, which is why sometimes this is taught when you do limiting reagents, which is a great way to do it, by the way. You get all the answers you want in like 2 seconds. But when you use those coefficients, that is basically doing the mole-to-mole relationship. So this is why you do need a balanced equation, otherwise, or reaction there. Otherwise, this is not going to be correct. And you do have to use the coefficient. Obviously, on the first one, our coefficient is 1, so we don't need to put minus 1x. We just go minus x, which represents obviously 1x. On our product side, we also have a coefficient of 1. So this would be plus x in this case. So again, really important to take that coefficient into account. When we get to equilibrium, which is the E part of it, we're just going to basically carry everybody down. So this is going to be 4 minus x. I'm going to get rid of the molarity symbol there so it doesn't get too mixed up in everything. And we'll end up with something like this. First off, any questions on the ice tip? So how do we solve for x in this case? We would use our equilibrium expression, and we would go k is equal to AB2 divided by the concentration of A and the concentration of B squared, and that equals 62 in this case. So putting in our values in this case, we would put our equilibrium line, and we actually would put it into here. And if we did that, we would end up with here x on top divided by 4 minus x and 2 minus 2x squared, and that would equal 62. I clearly just made up some numbers here. It didn't work out so well for me. I made up one here, but at this point, the goal would be to solve for x. And once you solve for x, the value of knowing what x is it will be, when you get this x, it will be this x, and this x. And what that's going to allow you to do is basically figure out what everybody's equilibrium concentrations are, because now you have numbers, right? You can just plug it in there and take 4 minus x, 2 minus 2x, and x, and you'll now have basically everybody's numbers. Now, the one I kind of did here would be a little bit super complicated, which so we won't finish this one out or anything like that, since I made up some numbers here. But there are a couple ways that we can solve for x, and one of the ways that we solve for x is with the quadratic. Yeah. Quadratic formula, as you may know, would be to simplify everybody down to an equation that looks something like this. Ax squared plus bx plus c equals 0. And we use these a, b, and c to go into our quadratic formula of x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Yeah, and that's where we get our a, b, and c values from. If you've done the quadratic before, you will know you get how many x values? You get 2 x values, right? And that's because you do this plus one way, right? And then you come back and do it minusing, right? The plus or minus, basically what that means. When you get 2 x values, number 1 or number 2, one of these values will not make sense. And what I mean by that is you will take one of those values, you will put it back into the equilibrium line, and in most cases, you'll end up with a negative number, which is not a good thing, right? Negative number can't have a negative concentration or pressure. So if you put something back in there and you get a negative number, that is not the correct choice. You should probably choose the other one. Now, when you get your 2x values here, you could end up with 2 positive values. You could end up with 2 negative values. You could end up with a positive and a negative value. So there is all those options of solving the quadratic and getting it. Any questions on that there? So let's see. There, by the way, are some other ways to solve for x, but this is a very common way to do that. So let's take a look at one here together and go through it and just to kind of see what we're talking about. So let's say we have this reaction here and K equals 7 in this case. And we're starting with an initial concentration of 0.663 molar for Br2. What is everybody's equilibrium concentrations? So the first thing I might want to do is write my equilibrium expression, which is the concentration of Br, and we're going to square it, divided by the concentration of Br2, and that equals lucky number 7 in this case. Now, I'm going to do my ice table, so I have my equation here. Initially, the only thing given to me is the concentration of Br2, which is 0.663, and this is 0. Now I'm going to go into my change, and my change is going to be minus x, and I know that this reaction is heading in this direction because we only have reactants, so there is no option for it to go in the other direction. I know this should be plus 2x. Once again, I do need to take the coefficients into account on the change part of it. That is really important. At the end here, we will end up with 0.663 minus x and 2x. Questions on the ice table here. We're ready now to solve for x, so we're going to take our equilibrium line and basically put it into our expression. And when we do that, that's going to give us 2x squared divided by 0.663 minus x equals 7. Now we're just going to do a little math here, right? So up on top, we want to make sure we also square the number, not just the letter. Yeah, so that becomes 4x squared, not 2x squared. Super common error people make. Here we need to multiply this to the other side. So I actually don't need the little line anymore since I'm going to multiply that to the other side. And when I multiply that to the other side, that is going to give me 0.663 times 7, which is 4.641 minus 7x. The goal here is to get this into the quadratic sort of equation, and that means we need to get everybody to one side. Does it really matter which way you go? No. Most people keep the x squared positive, but it doesn't really matter. But most people will keep the x squared positive. So I'm going to take everybody on this side and move it to this side. We do the opposite function. So that will give me 4x squared plus 7x. That's like a minus 7. That can become plus on the other side. This is a plus, which becomes a minus on the other side. Yeah, so opposites gives me 0. This is now my A, B, and C in this case. And this is what's going to go into my quadratic of x is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. So if we put these numbers in, we will get minus b, which is minus 7, plus or minus. If you do everything that's inside the square root, you take b and you square it. Then you subtract it from 4 times a, which is 4, times c, which is negative. You do need a negative there on c, 4.641. You will get inside the square root 123.256. If you then square root that, you will end up with 11.10. So again, I just put the numbers in, got what's inside, square root it, all divided by 2 times a, which is 2 times 4, which is 8 in this case. At this point, we need to do it twice, so I'm going to do the adding part first. So I'm going to take minus 7 plus 11.10 divided by 8 will give me an x value going the positive way of 0.513. I am then going to go back and do the subtraction here instead of adding. I'm going to go minus 7 minus 11.10 divided by 8, going to give me a negative 2.262. First off, any questions on how I got those numbers there? All right, so one of these should not make sense to us. and the one that hopefully you could just right away see shouldn't make sense is these are the two potential x values that we would put here. And obviously, if I took this negative number and put it into here, I'm going to end up with a negative concentration, right? And that is no good. That means that the good number here that we should use is 0.15 or 0.513, which will not hopefully give us a negative number. So that's going to be our x value. Now that we have our x value, we could go to our equilibrium line and actually solve for their concentrations. So the concentration of Br2 at equilibrium is 0.663 minus x, which means it is 0.663 minus 0.513. That is going to get us 0.663 minus 0.513, 0.150 molar. And if we do our Br at equilibrium, that is equal to 2 times x, which would be 2 times 0.153. And that's going to get us a 1.0, I'll call it 3 in this case, molar as well. First off, question on that. Those would represent the equilibrium concentrations of each of these guys here. Any questions? This is math, right? Everybody loves math. But it also means I could check to make sure I didn't screw up my math. This is not super complicated, this quadratic, but some of them are quite complicated. How could I check that I didn't screw up? If I take my equilibrium concentrations, which I now have, and I put it into this expression, what number should I get? Should get 7, yeah, or pretty close to 7 with rounding. So you could check yourself at the end by putting the equilibrium concentrations back into the equilibrium expression. If you do so in this case, I think you get like 7.0, something like that, which is 7. And you should be pretty close. It may not be exact, but it should definitely be in the ballpark. If you put it back in, you got like 400, you screwed up somewhere, yeah? And it can happen along the way. Any questions on that there? All right, we're going to lay it up there. It's good stuff.